So this is Jack's code. I just copy pasted it. Give me a second. I just need to open it again. I'll just go to where am I going? To to Trello. Yeah, here you go. Cause I keep the URLs in here, so I remember. So I copy pasted the code from here, and this one. So first I want to try see if that works. Then we're gonna try to kind of go through the code, see. But I think it's a rather simple code, so I think it should be fairly easy to understand. So we'll probably go ahead and then maybe scan the paper as well from Guillaume. Um, so basically, let's first. I think I got everything that I need, so I just think that's it. Basically, I put it in here, and I think I can just do that. See if that runs. Anyhow, um, okay. So there is an array of numbers that's caused by the print here. One of those numbers, state is the result of running the circuit, and then running the circuit. It's basically is this basically going to give you? I'm not familiar with strawberry fields, but I'm assuming. I mean, here you've got the initial state. Here you've got the different gates. I'm not familiar with the notation here, but I assume that is indicating the Q mode where this is being applied. And then you're measuring X, so the position quadrature, and then you're running the circuit, and then that's the result you get. So I'm assuming those results that we see in here are the sort of the optimal. I cannot zoom in. The optimal X values, the peak X values for the different parameterized circuits. So according to Jack here, I wonder where he's taken those things from. I guess he's generated them, but quadrature plots when I run the algorithm with A equals 1. I was able to generate this graph by inputting optimized parameters yielded by my program to the strawberry fields interactive simulation interface. Oh, I can double check that. We can double check that. This interface in here. So the x quadrature is located around x equals 1, which is expected optimal value of our function. Keep in mind that that does not work a lot of the time, as not all values of alpha and beta actually lead to circuits that correctly find the optimal value. These values have to be chosen based on the context of the problem being solved. Because I see a lot of numbers that are... How can I sort things in Python? Python sort array ascending. Not at least an array. But maybe that's the same thing. Ascending or descending? Sword. Okay. Like that. Okay. So if I just sword, if I just sword it and print it, what does this give me? Oh, come on. So uh, I guess it's not a list. Or I guess I'm using not the right instruction for that. None. Do. I mean, that's pretty basic. I don't know how to do it. How do you sort things in Python? Is it because I'm... not in Python? Oh. Doesn't return a new list. Okay. So basically, I just do this and that should work. Noob. Okay, cool. Let's go ahead. But I wonder why some values are actually below 1. The optimum is supposed to be 1. But at the point where like above 1.5, 1 point something. Anyway, but it works. It works. What's the Python count elements in list? Simply count, right? If I add, I'm curious. So that should be that doesn't work this way. Oh, I must. That's just probably size. It's probably like something like size. Or length. Come on. Come on. Oh, that's so basic. Python. I mean, I've never used Python really. Python. Least length. Len. Come on. Len. And uh, oh, I'm dumb. I'm dumb. Okay. No. 100. So there's 100 values. Just wanted to verify. This is testing trials. 100 here. Iterations 45. What is iterations used here? So it's used. Okay, so let's quickly go through this. Not so sure what's this. Um, it's from Strawberry Fields, I guess. Okay, so here basically is a catalog of, it's a list of your possible parameters. Um, Parabolic mean, which basically in Jack's post, I think he says I think he mentions he's using 1 or something like that, or 2 parabolic mean. I mean, there's 3 here definitely. This is our A. Yeah, but that doesn't matter really. And so, this is the what is the optimal value? What is math infinite? Okay, cool. I didn't know you could do that. Simulation. So you've got the function to optimize, and this is basically that. So this is that, your function. Then this is the run circuit thing. So and the article explains how Jack basically comes up with that particular circuit. So this is going to be the topic for the next video, because I'm going to then dive into the paper from Guillaume as well, and all the other material he's been sharing in Twitter around this topic, and then alpha parameter, beta parameter, where they're all 0.5. Why are they initialized as 0.5? Possible parameters. Where is possible parameters used? Alpha parameter, beta parameter. So basically, what this does is it picks randomly one of the possible parameters. Alpha. And then but then it runs circuit. Oh, so each each of these gates, because I thought beta and alpha would be the same for all the different steps or layers, because this is definitely ZPR, ZPR, so there's definitely sort of 3 layers of the same in here, right? And I don't know if this is the way this was intended, because, or I mean, I assume so. Just Jack talk about this here, I think. So he says that we have to consider how I'll implement this unit trace, and then he basically says, okay, there's the operations PZ and R, which then you can find the sort of the mathematical equivalence to the function you're trying to approximate in here. I mean, to the unitary here, and but I guess one thing that is not, so where alpha parameter are a set of parameters and probably means are sort of a after this. I guess the one thing here is there's one thing implicit. So there's one thing in here which is not in the article, but I think because so basically this is, so one of those, so those just 3 gates could be enough, right? But you can repeat that process over and over again, so you can actually have more layers of that. Then kind of finding how many layers that you want to have is really up to you as well. So what and what Jack is doing is for each layer, the actual beta and alpha parameter might be different because it's randomly chosen from this list, and I wonder whether that's something that is done on purpose, or I guess one of those things that, I mean, it's one of those trial and error things when you design such circuits, right? But in theory, can I just comment things like that in Python as well? Not much. I mean, I can just get rid of that, right? Because I could just get rid of that, and then it might. I mean, it'll definitely give me different set of results, but which we could compare, and then anyway, and then measure x, and then run Gaussian. I think this is because those gates are only Gaussian gates, and so I think Strawberry Fields, for some reason, you gotta specify in what mode you're running. There was something about the Fox space as well. I don't remember. I remember those words just roughly from a while back. Okay, but that's basically what's going on here. I think, as I said, the code seems to be fairly simple. So you iterate over the amount of iterations, which is 45. Result grid for age in range and the amount of shots, which is 10 shots. Run the circuit. Okay, so it basically gets the average of the 10 shots, then makes the calculation. Function optimize. Then what is this used for? Nowhere. I guess this tool, I guess this might be a trace that he used the code, because he says he then used some of those alpha embedders to basically go and get those things out of the interactive thing. The circuits I used to generate these 3 graphs. First step of the algorithm, second step of the algorithm, third step of the algorithm. Okay. After 3 steps, the peak of the x-coordinate is located around So these are the 3 steps, but the reason behind 3 steps is just purely it's a design choice. It's not, and I guess he's using that to probably retrieve the parameters used, so then he could play with the actual interactive. And then says if calculation is below the optimal value, so then we kind of got a new minimum. Then simulation. So, and what is simulation? Okay. Okay, so he's definitely tracking some more information in here. Greed. So what is the greed, by the way? Append hello, result hello. Okay, simulation, optimal value. DX measurement, result. An OP, okay. Optimal parameters. You see, so he's tracking. Oh, okay, cool. So he's actually tracking the optimal parameters, so he can then go and play with the strawberry fields interactive thing, which we can try and do. Okay, and then you just go over again. Okay. Search for the optimal value. Yeah. Aha, so what you get, wait a second. So what you're running here is already the optimal circuit. Cool, okay. Now I get it. And then, despite the fact that you're using exactly those set of optimal parameters, you can see that every time you get something different, right? So this outcome is already because then it's testing trials, it's not used anywhere else. Okay. So basically he's using the so these are already the results using the optimal parameters. Okay, so if I print optimal parameters, what is how do you comment in? Okay, like that. So if I just say print optimal parameters, and now I'm gonna go and get those. Here you have. So those are the optimal parameters, which if I do that again, they might be slightly different. Yeah. Actually, pretty different. No, I mean here there's a bit of a different. Yeah. Interesting. And if I would then print the smallest result, interesting. Okay. How to interpret that result though? Is this the around x equals 1? So if that's your I don't know, I'm curious. It's just with a equals 1. Ah, okay, so a equals 1, so sorry. So let me, because I want to try to reproduce that as closely as possible to what he's. So let's put the parabolic minimum to be 1, and let's run this again. Now, because this is how those graphs are based, what those graphs are based on. So they're based on basically a being equal 1, and then around x, which is the expected optimal value for our function, exactly, and minus 1. 1.2. I'm not getting numbers close to 1. That's a bit weird. Minus 1.85. Oh, question is this x or is this the result of the? That's x. That's not the result of the function optimize, right? I'm not sure. I'm not sure those results make sense to me, but so. And that's supposed to be this. That's supposed to be the smallest. Not length, but the array actual. Okay, I'll probably do another round on this. So I'm not getting values close to, and I'm using a equals 1, the parabolic minimum. But basically, what I could do. So, we just expect. Keep in mind that doesn't work a lot of the time, as not all values of alpha and beta actually lead to circuits that correctly find the optimal value. These values have to be chosen based on the context of the problem. Yeah, but a lot of the time, it's really a lot of the time. Strawberry Fields interactive simulation. So, Strawberry Fields. Ah, come on. That's Xanadu, I guess. Yeah. See if I could get the Strawberry Fields. I want to get in here. I think I had an account. Interactive. No, Blackbird. That's it. So what basically gates, settings, quantum modes. Mode length. What is this value? Change the value of h's and definition of the x and p operators. How is that set though? Because okay, so that's something that's not clear to me, but I don't see this being set here anywhere. But so basically, squeezing gate, squeezing factor, simulation time fog, Gaussian fog TensorFlow, cutoff dimensions, outputs quadratures. Interesting. Squeezing factors. I think the squeezing factors are basically minus 0.5 and 0. How can I minus 0.5 and 0? 0.5 and 0. And that will be, so we'll just do one mode for now because I'm running out of time as well. So can I just get rid of this? Come on. Ah. Minus 0.5 and 0, and it's a Gaussian, and it's cutoff dimension 5, and we want the quadratures. And we now basically go ZPR, yeah, ZPR. ZPR, and then there's a measurement X. And the Z, so for the Z parameter, and here we're going to use the 0.9 and the 0.5. 0.9. I know it's the parabolic minimum times 4 times the beta parameter. Okay. The parabolic minimum is basically, in this case, 1 times 4. So it's 4 times the beta parameter. So 4 times 0.9, it's 3.6. So this would be 3.6 for the Z. For the P, we're going to use minus 4 times the beta parameter. So minus, here was 3.6, so this is going to be minus 3.6. And for the R gate is minus 1 times the alpha parameter. And we say the alpha parameter, 0.9, sorry. The alpha parameter is minus 0.9. For R, assuming that's the correct thing. But then the beta parameter is 0.5 in here. It's 0.5. So that's the wrong calculation. This is 2. Okay. So it's 2. So this is going to be 2, and this is going to be minus 2. Correct? So we've got squeezing parameter, we're squeezing the Z gate, the P gate, the R gate, and the next measurement. And we'll say go. Okay. That's definitely not what I expected. Okay, but basically, I think basically that's where, because I see they're all the same, and that's not what Jack is getting. So I might be, even for the first step of the algorithm, that's what we're getting. So I might be doing something wrong. Okay, but that's going to be definitely then on the next video. try to kind of get those results back, the same like Jack is getting, because otherwise something's a bit off in here. But it's probably me. But cool, nice.